Today we will be doing electric field and potential. As you know that atoms consist of electrons, protons and neutrons. If you consider the charges on them, then the charges are, for electron it is minus 1.6 into 10 to the power minus 19 coulombs. For proton it is 1.6 into 10 to the power minus 19 coulombs. Neutrons do not have any charge. And if you consider their masses, the mass of electron is 9.1 into 10 to the power minus 31 kg. The mass of proton is 1.67262 into 10 to the power minus 27 kg. And mass of proton is 1.67493 into 10 to the power minus 27 kg. As you can see that proton and neutron mass is almost the same. Now the charge of an electron is considered the fundamental unit of charge. This means that all charges in the universe are integer multiples of charge of electron. So any charge of the universe will be an integer multiple of charge of an electron. Like say for example, if I have a charge equal to that of 2 protons, then I can write it as minus 2 into minus 1.6 into 10 to the power minus 19. So this will be the charge equal to 2 protons. So n is any integer, it could be positive, it could be negative, and it could also be 0, because you know that there are a lot of bodies which are not carrying any overall charge. Now this phenomenon that any charge can be written as integral multiple of electronic charge, this phenomenon is known as quantization of charge. So quantization of charge states that all charges are integer multiples of electronic charge, and therefore the electronic charge is the fundamental unit of charge. Now this particular chapter has a very, very important law that is called Coulomb's law. Suppose there is a charge Q1 and another charge Q2, and let us say that their separation is equal to R. So the charges are Q1 and Q2 and their separation is equal to R. Then the force between them is given by vector F equal to 1 by 4 pi epsilon naught into Q1 Q2 by R cube into vector R. Now vector R basically is the vector directed from one charge to the other. Like say for example, when I am considering the force on Q2, then vector R will be directed like this. This will be the direction of vector R, and that means the vector R will point either towards Q2 or away from Q2. And similarly, when I am considering Q1, then vector R will point like this. So if these two charges are of the same type, like both are positive or both are negative, then vector R will point towards that particular charge. That means it will be a repulsive force. But if Q1 and Q2 are of opposite nature, one is positive, one is negative, then vector R will point away from the particular charge. That means the force will be attractive. So this equation is known as Coulomb's law. In this equation, we have used a constant epsilon naught. Its value is 8.85 into 10 to the power minus 12 Newton (8.85 to 10 to the power minus 12 Coulomb square per Newton meter square. Now epsilon naught is called permittivity of free space. Free space is what we call vacuum. So epsilon naught is 8.85 into 10 to the power minus 12 Coulomb square per Newton meter square, and epsilon naught is what we call permittivity of free space, which basically means permittivity of vacuum. Now, which basically means that whatever is written over here is applicable if these two charges are in vacuum. Now suppose these two charges are not in vacuum. In that case, the formula will become one by 4 pi epsilon Q1 Q2 by R cube into vector R, and here epsilon is K times epsilon naught, where K is called the dielectric constant of the medium. So if these two charges are not in vacuum, they are placed in some medium other than vacuum, then instead of epsilon naught we will use epsilon, and epsilon is K into epsilon naught, where K is called the dielectric constant of the medium. Just as epsilon naught is called permittivity of free space, so epsilon is called permittivity of the medium, whichever medium these two charges are present in. Now this equation or this equation, they are the vector form of Coulomb's law. But it is more convenient to use the scalar form. The scalar form, all you have to do is just take a modulus on both sides. So you get scalar form of Coulomb's law, which is this. F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. And this is in case of vacuum, and if it is a medium other than vacuum, then 1 by 4 pi epsilon Q1 Q2 by R square if it is in some medium and not vacuum. So these two are the scalar forms of Coulomb's law, and in fact they are easier to use in the numericals. Now, let us come to the next concept in this chapter, that is called electric field. You see, you have suppose two charges, Q1 and Q0, and the distance between them is R. So the force on Q0, we will assume vacuum, is 1 by 4 pi epsilon naught Q1 Q0 by R square. Now if you divide both sides by Q0, you will get 1 by 4 pi epsilon naught q1 by r square. So this is known as the electric field at the point P. So the electric field is basically the force per unit, we call it test charge. Q naught is called a test charge. It has been placed over there to analyze what would be the force on it and then divide that force by the charge. So we can say electric field at a point P is the force per unit test charge at that point P. Now, why do we need a term like electric field when we already know electric force? What happens is that in certain situations, we are more interested in a particular point in space because electric force is between a pair of charges, whereas electric field is for a particular point in space. So once I know the electric field at a point, all I have to do to analyze the force on any charge at that point, I just need to place the charge and multiply it with the electric field. What I mean to say is that if you consider this in a vector form, then this is the definition of electric field in vector form. So you have taken a test charge Q, found the force on it and then divided the force by Q. You could also write this as vector F is equal to Q into vector E. So this is a very, very handy equation which in fact helps us to directly find the force once we know the electric field at a particular point. And you will notice that this has an analog in gravitation. In gravitation, you have studied that if you are considering any planet like the Earth, then the gravitational field of the Earth, you know, is called G, small g. So the force on any mass m will be force equal to mass m into vector g. So this is the electrostatic analog of F equal to mg, and it is F equal to QE. So electric field definition seems to be that find the force on a test charge and divide the force by the test charge to get the field at that particular point. However, this definition of electric field needs another addition to make it perfect. The test charge itself is not described properly. What is this test charge? What is its value? The correct description of test charge should be that it is as small in magnitude as possible so that it does not disturb the other charges present in that region. So the correct definition of electric field should be electric field is equal to the limit of force per unit test charge when the test charge is of extremely small magnitude, or you may say it is the limit of F by Q naught as Q naught tends to 0. So this in fact is the perfect definition of electric field. For practical purposes or for numerical computations, this is good enough for us to understand what electric field really is. This in particular is very useful for doing the numericals and the calculations, this particular form of the relation between electric field and electric force. But if you want to know the definition, then this is the correct definition, that it is the limiting value of the force per unit test charge when the test charge is of extremely small or smallest possible magnitude. Now, the thing is that electric field is something which can also be given a geometrical interpretation. Say for example, you have an isolated charge Q, let's say it's positive charge. So to understand the electric field around this charge, you just have to visualize a positive test charge placed over here. Obviously, that positive test charge will get repelled, and the repulsions will be directed as per these arrows. Now, these arrows are called lines of electric field, right? And they are also called lines of force. So, what exactly is a line of force? It is it gives the direction of electric field at any point in space, and to obtain it, all we have to do is we have to visualize a positive test charge placed at that point. So, like I said, the actual definition of test charge is that it should be of as small magnitude as possible, but at this point in time we just need to know the direction of electric field. So we'll just say that if you place a positive test charge, then the force on that will be directed along these arrows. So these are called lines of force or lines of electric field. What will be the nature of lines of field if this charge is negative? Obviously, this will be the nature. The lines of electric field or the lines of force will point towards the negative charge. So if I have a negative charge minus Q, then the lines of force or lines of field will all point towards this negative charge. Let us say you have two positive charges. In that case, the lines of force will point like this. So if you have two positive charges placed in front of each other like this, then this will be the manner of the lines of force or the lines of electric field, the way I have shown it in the board. And if you have one negative charge and another positive charge, then the lines of force will point like this. So these will be the lines of force. If you have a negative and a positive charge placed near each other, then these will be the lines of force. Now these lines of force, all of these lines of force have some properties, and now we will just discuss what are those properties. So the first properties is that the lines of force originate from positive charges and terminate on negative charges. Let's have a look. If you consider a 1 meter by 1 meter square very close to the charge Q, you will see that the lines of force are densely packed. And if you consider an identical 1 meter by 1 meter square farther away from the charge q, you will find that the lines of force passing through this will be less densely packed. So the relative closeness of the lines of force indicates the relative strength of electric field. That means we can conclude that the electric field over here will be much stronger than the electric field over here. So this is point number 5. The next point, the lines of force have a tendency to contract in length like a stretched spring. So you will observe one thing, that the negative and positive charge, the lines of force between them, they tend to contract in length. That means what? The lines of force are directed in such a way, since the length between the positive and negative charge is fixed, so they tend to follow a path which suggests that they are trying to contract in length, and in fact you will find that due to that they are expanding laterally. So laterally they seem to be expanding, lengthwise they seem to be contracting, and in fact this explains the attraction between opposite charges. These two charges are opposite and they attract each other because the lines of force tend to contract along the length. Now the next point is precisely the similar point as the previous one, that lines of force tend to separate from each other in the direction perpendicular to the length. So you will notice that in this diagram both charges are positive, so the lines of force are trying to separate from each other, like this is the length, so in the perpendicular direction they tend to separate from each other. So that expand laterally thing which I said over here, you can see it more pronounced over here, that in fact they are actually separating from each other, and this explains the repulsion between opposite charges. Apart from this, you also need to remember one thing, that lines of force, when they come out of a positive charge, they come out normally, and when they enter a negative charge, they enter normally. They come out normally from a positive charge and enter normally into a negative charge. Another thing which you have to remember is that electrostatic force is a conservative force, so the lines of force cannot form closed loops. They cannot form closed loops. So if they start off from a positive charge, they have to terminate on a negative charge. If no negative charge is present, they will not terminate. They will just go outward from the positive charge. But they cannot form closed loops because electrostatic force is a conservative force. So this is the topic, lines of force. And as an addition to this discussion, we can also add another diagram. So if you want to find the electric field due to a uniform charge distribution, this is a uniform line of force, uniform line of positive charge, and the lines of force are perpendicularly away from this uniform line of charge. So this is the topic, lines of electric field. Next we come to electric potential energy. Electric potential energy. Suppose there are two charges, Q1 and Q2, and these two charges are being separated from each other. So at some point of time during their separation, the separation between them is r, and from that moment onwards the separation is increased by dr. So I repeat, there are two charges q1 and q2, and they have an initial separation which is given, and then they are separated further from each other, and at some point of time during their separation the distance between them is r, and from that point onwards the separation between them is increased further by dr. Now in this particular diagram, the force between the two charges will be F is equal to Q1 Q2 by 4 pi epsilon naught r square. This will be the force between the two charges as per this diagram. Now, keeping this in mind, if the force undergoes a further displacement, then the work done will be Q1 Q2 by 4 pi epsilon naught r square into dr. So if this is the force, then this will be the work done by the force. Now the work done by a force is equal to the negative of change in potential energy, or you may say that the change in potential energy is negative of work done. So it is minus of Q1 Q2 by 4 pi epsilon naught r square into dr. From where did we get this result? If you remember, this result was a part of class 11 work energy chapter. We defined change in potential energy as negative of work done by a conservative internal force. As you know that electrostatic force is a conservative internal force, so du is minus dw, that is minus of q1 q2 by 4 pi epsilon naught r square into dr. Now if we integrate from R1 to R2, if we integrate minus Q1 Q2 by 4 pi epsilon naught r square from R1 to R2, we can say that this integral is equal to final potential energy minus initial potential energy, that we can write it as U2 minus U1. Now you know that the result of this integration is Q1 Q2 by 4 pi epsilon naught r from R1 to R2, and once you apply the limits, you will get Q1 Q2 by 4 pi epsilon naught into 1 by R2 minus 1 by R1. Now at this stage we need to define the reference potential energy. Now it's pretty clear that when you put R1 equal to infinity, then this term vanishes. So the reference potential energy is R1 equal to infinity, U1 equal to 0. So if the two charges were initially at a separation of infinity and finally they are brought to a separation r, then the potential energy of the system of the two charges is U equal to Q1 Q2 by 4 pi epsilon naught r. I repeat again, if the two charges Q1 and Q2 are brought from an initial separation of infinity to a separation r, then the potential energy of the system of two charges is U equal to Q1 Q2 by 4 pi epsilon naught r. If you want to give a purely physical description of potential energy, you can say that it is the work done by some external agent in bringing the two charges from an infinite separation to a separation r. So this is the absolute definition of potential energy, considering the potential energy for infinite separation as 0. Now, if you have a charge Q0 at a point P and another charge Q such that their separation is R, then the potential energy of the system will be Q0 by 4 pi epsilon naught R. As you expect, the potential energy of this system will be given by this formula. If you divide the potential energy by Q0, then the expression which you get, this expression is called the potential at the point P. So, for a pair of charges, we can have potential energy, but if we are more interested in analyzing a particular point in space, then potential is a better definition, a more versatile term. So the potential at the point P is the potential energy of a system per unit test charge between the test charge and another charge Q, and the expression of that is Q by 4 pi epsilon naught R. If you want to give a purely physical definition of potential at a point, you can say that it is the work done by an external agent in bringing a unit positive test charge from infinity to that particular point. So this is the term potential. Now, suppose you have a region in space where the field is given by E. Let's say you have a region in space where the field is given by E. So, if a charge Q is placed in this region, then the force on that charge Q will be F is equal to Q into E. Now, let us say that this charge undergoes a displacement of dr, so the work done will be equal to QE dot dr. So if the charge Q undergoes a displacement of dr, then the work done will be equal to QE dot dr. Since electrostatic force is a conservative force, the change in potential energy will be equal to negative of work done, that is equal to minus of QE dot dr. So the change in potential energy when the charge Q is moved by a distance dr is given by du equal to minus QE dot dr. Now if you divide du by Q, then you will get du by Q equal to minus E dot dr. But you know now that du by Q is known as potential, and therefore the change in potential is minus E dot dr. Now remember, this du is the change in potential energy, and therefore dV is the change in potential. Now if the charge is being displaced from an initial position vector r1 to a final position vector r2, then the change in potential, you can say V2 minus V1, is integral r1 vector to r2 vector minus E dot dr. So V2 minus V1 is minus r1 vector to r2 vector E dot dr. So this is the change in potential when you are shifting the charge Q from the location r1 vector to r2 vector. Now how do we use these formulas First of all, this formula, this one, V2 minus V1 is equal to minus R1 to R2 E dot dr. This formula is used in those situations where we know electric field but we do not know the potential. So by using the field, we can calculate the potential. So this formula is used in those situations. The formula dV equal to minus E dot dr, this formula is used when we are only concerned with the change in potential. We are not interested in the absolute value of the potential at any point. We just need to know the change in potential. Then we use this formula. In fact, this formula has a very interesting corollary. Suppose you express the dot product as dV equal to minus E dr cos theta. You will see that when theta is 90 degree, dV is 0. This physically means that suppose the charge q is moving perpendicular to the field. Physically, this means that suppose the charge q is moving perpendicular to the field, so when it is moving perpendicular to the field, the change in potential of the charge q will be 0. So that is the physical meaning of theta equal to 90, dV equal to 0. Now, if you can join all such points where dV is 0, then you will get a surface called equipotential surface. So the definition of equipotential surface is, it is the locus of all points having the same potential. In fact, if you have a isolated positive charge, then any sphere centered about the charge, any sphere centered about this charge will be an equipotential surface. Because if you draw a sphere centered on this charge, you can see that the field will point radially outward, whereas if you consider a tangent to the sphere, that will be perpendicular to the field, and that is why every point on the surface of this sphere will have the same potential, because between any 2 points dV will be 0. So this is a very, very important corollary of the formula dV equal to minus E dot dr. There is another way to use this result dV equal to minus E dot dr. I was telling you that you may know the field, but you need to find the potential. Sometimes the converse may happen. You may know the potential and you may need to find the field. In that case, we will begin by initially writing the field as EXI plus EYJ plus EZK using orthogonal vectors IJK, and we will write dr as dxi plus dyj plus dzk. So the field will be written like this and dr will be written like this. Now, if you use dV equal to minus E dr, this is what you will get. dV equal to minus Ex dx minus Ey dy minus Ez dz. Now remember what I told you, we are trying to achieve a result which will help us to find the field if we know the potential. How do we do that? First of all, imagine y and z are constant, then dy and dz will become 0. In that case, Ex will be minus delta v by delta x. Now when do we use the symbol delta? The symbol delta is used whenever you are doing partial derivative. So dv and dx are derivative of v with derivative of v and derivative of x. But if you do partial derivative, that means the other variables are being treated like constants. So if you consider y and z as constant, then ex will be minus del v by del x. Similarly, ey will be minus del v by del y, and ez will be minus del v by del z. So we are able to now find ex, ey and ez. Once we know the values of ex, ey and ez, we can put them over here to find the field. So the method of finding the field using the value of potential is through partial derivatives, and these are the results which you need to use and then apply over here. The next topic is electric dipole. Suppose you have two charges minus q and q placed at a separation d. So there are two charges minus q and q, and the separation d between them is considered to be very, very small. So this combination is called a dipole. Every dipole has a dipole moment associated with it. The dipole moment is a vector. So vector p is q into d, and the direction of d is from negative to positive charge. So the dipole moment vector p will be q into vector d, where vector d is directed from negative to positive charge. Now, in case of electric dipole, we will be now deriving two formulas. One is potential at any point due to a dipole, and the other is field at any point due to a dipole. For potential due to an electric dipole, this is going to be our next calculation, potential due to an electric dipole. Suppose you have a dipole and P is a point where you are interested in finding the potential. So what you do is you join O to P and you produce the join of OP backwards and drop two perpendiculars, one from A to A dash and the other from B to B dash, and finally you join AP and BP. Now in this diagram we will take this angle as theta and we will take OP as R. So this angle we will take it as theta and OP we will take it as R. So as you can see from this diagram that if the entire length of the dipole is D, then each of OB and OA will be half D, and in that case OB dash will be half D cos theta. OB dash will be equal to half D cos theta. Now, thanks to the fact that the dipole is very small, we can assume that BP and B dash P will both be equal. And you can see from this figure that B dash P is OP minus OB dash. So it is R minus half D cos theta. So BP will be R minus half D cos theta. Now let us come to AP. Now AP, as you can see from this diagram, is equal to A dash P. Again, that is because the dipole is very small, so we can assume AP equal to A dash P. Now in this diagram, you can see that A dash P is OP plus OA dash. OP is R. So OA dash, from this figure you can see that it is half D cos theta. So we know BP, we know AP. So therefore the potential at the point P will be 1 by 4 pi epsilon naught Q divided by R minus half D cos theta minus Q divided by R plus half D cos theta. Now, if you take Q by 4 pi epsilon naught common, then you will get D cos theta in the numerator and R square minus D square by 4 cos square theta in the denominator. Now we have been saying all along that D is very small and Q into D is dipole moment P. So P cos theta, and since D is very small, we can neglect the term D square by 4 cos square theta. So we are finally now getting the formula. Potential at P is P cos theta by 4 pi epsilon naught into R square. So this is the formula to find the potential at any point due to a dipole. Next we will do field due to an electric dipole. Suppose you have a dipole formed by two charges minus Q and Q, and you are interested in knowing the field at the point P. So let the field at the point P have a direction which we are not very clear about. Let it be this. So what we will do is, for our convenience, we will resolve the field into two mutually perpendicular directions. One will be called ER, that will be along OP, and the other will be called E theta, that will be perpendicular to OP. Now if you consider a small change of angle D theta, in that case if you call this point as P2, then PP2, OP is R, it will be R into D theta. So PP2 will be R into D theta. Similarly, you can consider a point P1 such that PP1 is dr. Now we will now try to find independent expressions for ER and E theta, and then we will combine them to get the resultant. So first of all, ER we can say is minus dV by PP1. Now when you are doing PP1, you know that PP1 is dr, but we will keep theta constant because along the line OP theta is constant. So it will be minus del V by del R. So we will get minus del by del R P cos theta by 4 pi R square. So this will give 2p cos theta divided by 4 pi R cube. So ER will be 2p cos theta divided by 4 pi R cube. Similarly, let us try to find out what is E theta. So E theta is minus dV by pp2. So that is minus dV by r into minus delta V by r into delta theta. So we will get minus delta by r delta theta into p cos theta by 4 pi r square. So after simplification, we will get p sin theta. We will get p sin theta by 4 pi r cube. So this will be the formula to find the field E theta. Now we know ER, we know E theta, so we can combine them and find out E. So E will be the resultant of both of them. So that is P sin theta by this should be 4 pi epsilon by 4 pi epsilon naught r cube whole square plus 2p cos theta by 4 pi epsilon naught r cube whole square. So this will be the value of the field due to the dipole. If you simplify this, you will get P divided by 4 pi epsilon naught r cube into root over 1 plus 3 cos square theta. So this is the formula to find the field at the point P. P divided by 4 pi epsilon naught r cube into root over 1 plus 3 cos square theta. Now, since the field is a vector quantity, we also need to know the direction. So the direction we can get from alpha. So we will take tan alpha is equal to E theta by ER. We already know E theta, we already know ER. So it's coming tan theta by 2. So tan alpha, the value is coming tan theta by 2. So this is the magnitude of the resultant field, and this is how to find the direction. Now there are two special cases. One is called end-on, or you could say end-on is also known as axial. So for end-on, you need to put theta equal to 0. So the field you can see will become 2p by 4 pi epsilon naught into r cube. If you just put theta equal to 0, then end on, or which is known as axial, the field will be this. The other one is known as broadside on, which is also known as equatorial. So for this, theta will be 90 and the field will be P by 4 pi epsilon naught r cube. So these are the two special cases. End on, which is known as axial, the field is 2p by 4 pi epsilon naught r cube, and broadside on, which is known as equatorial, the field is p by 4 pi epsilon naught into r cube. So this completes the topic field due to a dipole. Next we will be doing torque on a dipole. Suppose there is a dipole formed by the charges q and minus q, and there will be forces F1 and F2 acting on these two charges. So you can see that if these two charges are present in a field where the field is E and the angle made by the dipole with the field is theta, so what will happen is that the torque of F1 about O, the torque of F1 about O will be given by Q into OB cross E. So the torque of F1 about O will be given by Q into OB cross E. Similarly, the torque of F2 will be given as Q into minus Q into OA cross E. So this will be the torque of Q about O and minus Q about O. So the total torque will be the sum of these two torques, that is Q into E into OB minus OA. So this is coming Q into AB into E. But if you look at the diagram, Q into AB is the dipole moment. So the formula for torque is dipole moment cross E. So this is the formula to find the torque on a dipole placed in a uniform field. Now suppose you want to find the potential energy of the dipole in this situation. So imagine that an external agent has turned the dipole anti-clockwise by an angle d theta. So the work done by the external agent is torque d theta. So that is equal to minus, since you know torque is P cross E, so if you write it in scalar form, it is minus PE sin theta. Why this minus is there? Because you can see that if the external agent turns the dipole anti-clockwise, the torque will have a clockwise effect. So work done by torque is this, and you know that negative of work done by torque is equal to change in potential energy. So du is minus dw, that is P sin theta. So if you rotate the dipole from an initial angle theta 1 to a final angle theta 2, then u2 minus u1, change in potential energy, is Pe sin theta d theta from theta 1 to theta 2. Now after integration and substitution of limits, you will get Pe into cos theta 1 minus cos theta 2. Now remember, we are talking about potential energy, so again we need a reference value. So if you take theta 1 equal to 90 degree and u1 equal to 0 and theta 1 equal to theta and u2 equal to u, then you will get this formula, potential energy is minus P dot E. So the potential energy of a dipole in a uniform field is given by minus P dot E. So this completes the topic dipole, and it also brings us to an end of the chapter electric field and potential.